Namaste everyone and welcome to day 9 of our 15-day beginner data science sprint. In the previous lessons, we learned how to load data, clean it, transform it, summarize it and visualize it. Today we are going to take the next important step. We are going to learn how to describe data using statistics. But do not worry, this lesson is called statistics without heavy mathematics for a reason. We will not spend time proving formulas or solving complicated equations. Instead, we will focus on understanding what statistical values actually tell us about real world data. By the end of this lesson, you will be able to compare mean, median, and mode, understand range, variance, and standard deviation, interpret percentiles, identify possible outliers, calculate correlation, and explain statistical results in simple everyday language. The main goal is not just to calculate numbers. The goal is to understand what those numbers mean and what they do not mean. Let us begin with a simple question. Suppose 5 students receive these scores. Or let me write it here only. What would you say is the typical score? Most students score 50. But let us calculate the average. Add all the scores, that is 50 plus 50 plus 50 plus 50 plus 50 plus 100 equals 300. Now divide 300 by 6. The average is 60. But did most students score around 60? No. 4 out of 5 students scored 50. Only one student scored 100. That single high score pulled the average upward. So our opening question is, if one student scores 100 and everyone else scores 50, is the average a fair summary? The answer is sometimes yes, but sometimes no. The average gives us useful information, but it does not always tell the complete story. That is why we need to understand more than one statistical measure. Before writing code, let us understand where statistics fit into the data science workflow. We began with a question, then we collected or loaded data. After that, we inspected and cleaned the dataset. We selected useful columns and created visualizations. Now, statistics helps us summarize the patterns we have found. It helps us answer questions such as what is the typical score? So, statistics helps us answer questions like what is the typical score? How different are the students from one another? Are there unusually high or low values? How many students scored below a particular value? Do study hours and final scores move together? So these answers we can get by statistics. Statistics help us move from simply looking at data to interpreting it. However, statistics does not automatically provide the correct conclusion. We must still use context, caution, and common sense. Let us begin by importing the libraries we need. Create a new code cell and write import pandas as PD, import NumPy as NP, import Seaborn as SNS, and import matplotlib.pyplot as PLT. So before running the cell, you should have asked, what do you expect this cell to display? And the answer is probably nothing. The cell only imports the libraries. It prepares our notebook so that we can use their functions later. Let us now quickly understand the role of each library. Pandas help us work with tables and data frames. NumPy helps us perform numerical operations. Seaborn helps us create statistical visualizations. Matplotlib helps us customize and display charts. For today's lesson, we will use the clean student performance dataset from our previous lesson. Upload the file to Colab if it is not already available. Then write this command. So my file is here on the left side. Now let us inspect the first few rows. Before running this cell, ask yourself, what do you expect to see? We expect to see the first 5 rows of the dataset. Now run the cell. You should see columns such as student ID, study hours, attendance, previous score, final score, gender, and possibly other student related fields. The exact columns may depend on the dataset version you are using. The important columns for today are final score and study hours. Let us also check the dataset size. This tells us how many rows and columns are present. Remember that statistical results depend heavily on the available data. A result calculated from 10 students may be less stable than a result calculated from 10,000 students. Our first major idea is called center. Center describes a typical or central value in a dataset. The three common measures of center are mean, median, and mode. Let us understand them using a small list. Create this list. Now calculate the mean. Before running the cell, predict the answer. Every value is 50, so the mean should also be 50. Run the cell. So the result is mean 50. Now let us introduce one unusually high score. Calculate the mean again. Before running it, predict what will happen. Will the mean remain 50? No. The high value of 100 will pull the mean upward. Run the cell. The answer is mean 60. This shows us that mean is affected by extreme values. The mean is what we commonly call the average. It is calculated by adding all the values and dividing the total by the number of values. In everyday language, the mean tries to distribute the total equally across all observations. For example, scores equals 40, 50, 60, 70, 80. And let's calculate the mean. The output is 60. The mean is useful when values are reasonably balanced and there are no extreme values heavily influencing the result. However, the mean can sometimes be misleading when the dataset contains outliers. Consider income data. Suppose 4 people earn euro 25,000 per year and one person earns euro 1 lakh per year. The mean income would be much higher than what most people actually earn. So the mean may not represent the experience of the typical person. This does not mean that the mean is incorrect. It simply means that we must interpret it carefully. The median is the middle value after sorting the data. Let us calculate the median of our scores with an outlier. Before running this cell, predict the output. The sorted values are 50, 50, 50, 50 and 100. The middle value is 50. Run the cell. The output is median 50. Notice the difference. The mean was 60 but the median is 50. The median is less affected by an unusually high or low value. That makes it useful for data containing outliers such as income, house prices, delivery times, hospital waiting times, and website session duration. When the number of values is odd, the median is single middle value. When the number of values is even, the median is average of the two middle values. For example, value equals and print np.median values. The two middle values are 20 and 30. Their average is 25. So the median is 25. The mode is a value that appears most frequently. Let us calculate it using pandas. Before running the cell, predict the result. The value 50 appears 4 times. The value 100 appears only once. Therefore, the mode should be 50. Run the cell. You should see 0 and 50. Dtype in 64. Pandas return the mode as a series because the dataset can have more than one mode. For example, values equals pd.series 10, 10, 20, 20, 30 and print values.mode. Both 10 and 20 appears twice. Therefore, both are modes. The mode is especially useful for categorical data. For example, we may want to know the most common payment method, the most common product category, the most common city, or the most common performance grade. Let us find the most common final score in our dataset. This result tells us which final score appears most often. However, this does not automatically mean that the score is the best summary of the entire class. It only tells us which exact value occurs most frequently. Let us compare all three values together. Before running the cell, ask yourself: Do you expect the mean and median exactly to be exactly equal? They may be close, but they do not have to be equal. Now run the cell. Your exact values will depend on the data set. So our output looks like this. Mean is 64.487, median is 64.1, and mode is 62.5. Here is a simple interpretation. The average score is approximately 64.5. Half the students scored below 64 and half scored above 64. The most frequently occurring score is 62.5. Notice that each measure answers a different question. The mean answers what would each student receive if the total score was shared equally. The median answers what is the middle score after arranging the values. The mode answers which score appears most frequently. No single measure is always the best. The correct choice depends on the question and the shape of the data. Pause the video here. Without using technical jargon, explain the most important output from the previous cell in one sentence. For example, you might say the typical student scored somewhere in the low to mid 70s. Or we can say the typical student scored somewhere in the low to mid 60s. Try not to say only the mean is 62.4. That repeats the number but does not interpret it. A good data scientist translates outputs into understandable conclusions. Resume the video after writing your sentence. Center tells us where the data is located, but center does not tell us how different values are from one another. How different the values are from one another. For that, we need to understand spread. Consider these two lists. Group A equal to 48, 49, 50, 51, 52. And group B equal to 10, 30, 50, 70, 90. Let us calculate their means. Before running this cell, predict the results. Both groups are centered around 50. Run the cell. Group A mean is 50 and group B mean is 50. The means are identical, but are the two groups similar? No. Group A is tightly packed around 50. Group B is widely spread from 10 to 90. This teaches us an important lesson. Two data sets can have the same mean, but look completely different. That is why we need measures of spread. The range is the difference between the largest and smallest values. Let us calculate it for both the groups. So range A, range B. Then we print the values. Before running the code, predict which group will have the larger range. Group B should have the larger range because its values are much farther apart. Run the cell. The output is group A range is 4 and group B range is 80. For group A, 52 minus 48 equals 4. For group B, 90 minus 10 equals 80. The range is easy to understand. However, it uses only the smallest and largest values. It ignores everything in between. It can also be heavily affected by a single outlier. For example, if one incorrect score of 500 appears in the data, the range becomes very large, even if all other scores are close together. Variance measures how far values are spread from the mean. A low variance means that the values are generally close to the mean. A high variance means that the values are more widely spread. Let us calculate variance for both groups. Before running the cell, predict which group will have a higher variance. Group B should have a much higher variance. Now run the code. You should see that group B's variance is much larger. The exact calculation behind variance involves finding the difference between each value and the mean, squaring those differences, and averaging them. You do not need to memorize the formula for this beginner lesson. What matters is the interpretation. A large variance means greater spread. One limitation of variance is that its units are squared. If scores are measured in marks, variance is measured in squared marks. That makes it less intuitive to explain. For practical explanation, standard deviation is often easier. Standard deviation also measures spread, but it is expressed in the same unit as the original data. Let us calculate it. Before running the cell, predict the result. Group B should again have a much larger value than the cell. You may see results similar to Group A standard deviation is 1.4 and Group B standard deviation is 28. This tells us that values in Group A usually stay close to the mean of 50. Values in Group B are much more widely spread across around the same mean. In simple language, standard deviation tells us how much variation is typical in the data. A low standard deviation means that values are relatively consistent. A high standard deviation means that values vary considerably. For student scores, a low standard deviation may mean that most students perform similarly. A high standard deviation may mean that some students perform very well while others struggled. You may sometimes notice a small difference between Pandas and NumPy standard deviation. For example, run this code. The results may not be exactly equal. This happens because NumPy uses the population standard deviation by default, while Pandas uses the sample standard deviation by default. For now, you do not need to study the mathematical difference deeply. Just remember, when working with a data frame column using pandas.std is completely appropriate for our current analysis. The most important part is to be consistent and understand what the value represents. So the most important part is to be consistent and understand what the value represents. Now let us calculate the main statistics for final scores. Before running the cell, make 3 predictions. First, what do you expect the minimum scores to be? Second, do you expect the mean and median to be close? Third, do you expect the standard deviation to be small or large? Now run the cell. The exact output depends on your dataset. Suppose the standard deviation is around 12. A simpler interpretation could be student scores vary by roughly 12 marks around the average. Be careful with the word commonly. Standard deviation does not mean that every student is exactly 12 marks away from the mean. It provides an overall measure of spread. Also remember that a higher standard deviation is not automatically good or bad. Its meaning depends on the situation. In an examination, high variation may indicate unequal understanding. In a creative competition, high variation may be completely normal. Pandas can calculate many different important statistics at once using this type. Write print scores.describe. Before running the cell, predict what kind of information it will display. We expect to see count, mean, standard deviation, minimum, percentiles, and maximum. Run the cell. The output will look similar to this. Count is 120, mean is around 64, steady around 12, mean is 31, 25 percentile is 57, around 57, 50 percentile is around 64, 75 percentile is around 71, and max is 100. Your values may be different. Let us interpret each part. Count tells us how many non-missing scores were analyzed. Mean is the average. STD is the standard deviation. Mean is the lowest score. 25% is the 25th percentile. 50% is the median. 75% is the 75th percentile. Max is the highest score. This one method gives us a compact statistical summary of a numerical column. A percentile tells us the position of a value relative to the rest of the data. Let us begin with the 50th percentile. The 50th percentile is the median. It means that approximately half the observations are below this value and approximately half are above it. The 25th percentile is also called the first quartile. Approximately 25% of the values are at or below it. The 75th percentile is also called the third quartile. Approximately 75% of the values are at or below it. Let us calculate these values directly. Before running this cell, predict which values should be the largest. The 90th percentile should be larger than the 75th, 50th, and 25th percentiles. Now run the cell. Suppose the 75th percentile is 71. A simple interpretation is about 75% of students scored 81 or lower, while about 25% scored above 81. Suppose the 90th percentile is 89. We could say, or in our case, it is 79. We could say a student scoring above 89 is among approximately the top 10% of scores in this dataset. A student scoring above 79 is among approximately the top 10% of scores in this dataset. Percentiles are useful in examination rankings, income analysis, website response times, delivery performance, health measurements, and customer spending analysis. However, percentiles describe position within the dataset. They do not automatically tell us whether a score is objectively good or bad. Good or bad. Being in the 90th percentile means being higher than most values in that group. It does not necessarily mean that the values meet an external standard. The distance between the 25th percentile and the 75th percentile is called the interquartile range or IQR. It contains the middle 50% of the data. So IQR contains the middle 50% of the data. Let us calculate it. Before running the cell, predict whether the IQR will be larger or smaller than the full range. It should be smaller because it focuses only on the middle half of the data. Now run the cell. The IQR is useful because it is less affected by extreme minimum and maximum values. While the full range uses the two most extreme points, the IQR focuses on the central part of the dataset. An outlier is a value that is unusually far from the other values. For example, imagine these scores: 65, 68, 70, 72, 74, 76, 150. The value 150 looks unusual. It may be a data entry error, a score recorded using a different scale, a rare exceptional case, or a real observation that deserves investigation. This is important. An outlier that is not automatically a mistake. We should investigate it before removing it. In some cases, outliers contain the most important information. For example, an unusually large banking transaction may indicate fraud. An unusually high machine temperature may indicate failure. An unusually long hospital stay may identify a complicated case. An unusually successful marketing campaign may reveal a valuable strategy. Data cleaning does not mean deleting every unusual value. It means understanding whether that value is valid and relevant. A common way is a common way to identify possible outliers uses the interquartile range. The usual boundaries are: lower boundary equals Q1 minus 1.5 times the IQR. Upper boundary equals Q3 plus 1.5 times the IQR. Let us calculate them. Now identify values outside those boundaries. So we find no outliers. We may find no outliers, one outlier or several outliers. Remember that these are possible outliers according to a statistical rule. The rule does not prove that the values are wrong. It only tells us which values deserve closer inspection. A box plot gives us a visual summary of center, spread, and possible outliers. Let us create one. Before running the cell, predict what you expect to see. You should see a box containing the middle part of the data, a line containing the box, a line inside the box representing the median, lines extending outwards, and possibly separate points representing potential outliers. Now run the cell. Let us understand the chart carefully. This line inside the box represents the median. The left and right side of the box represents approximately the 25th and 75th percentiles. The width of the box represents the interquartile range. The lines extending from the box are often called whiskers. Points beyond the whiskers may be shown as possible outliers. But again, box plot does not tell us why a value is unusual. It only helps us identify where to investigate. A box plot gives a compact summary, but it does not show the complete shape of the distribution. Let us also create a histogram. Before running the cell, ask, do you expect the scores to be evenly distributed? Do you expect most scores to be concentrated around one region? Now run the code. The histogram shows how frequently different score ranges occur. The smooth line provides an approximate view of the distribution's shape. By using both a histogram and a box plot, we get a more complete understanding. The box plot summarizes center and spread. The histogram reveals the shape and concentration of values. This is an important data science habit. Do not depend on only one chart, one number or one chart. Use several complementary views. Statistics becomes even more important when we compare groups. Suppose the dataset contains a gender column. We can compare the average and median final scores by gender. Before running the cell, predict what the table will contain. For each gender category, it should show the number of students, the average score, the median score, and the standard deviation. Now run the cell. When interpreting this result, avoid making broad claims from small differences. For example, suppose one group has a mean of 63 and another has a mean of 65. The difference alone does not prove a meaningful performance gap. We should also consider the number of students in each group, the amount of variation, whether the groups were comparable, and whether the difference may have occurred by chance. At this stage, we are describing the dataset. We are not making a final scientific conclusion. Now let us understand correlation. Correlation measures how strongly two numerical variables move together. For example, we may ask, do students who study more hours tend to receive higher final scores? So this is our question. Let us calculate the correlation. Correlation equals df study hours dot for df final score, and then we print the correlation. Before running this cell, predict the sign of the result. Do you expect it to be positive, negative, or close to zero? Because studying more may be associated with higher scores, we may expect a positive correlation. Now run the cell. The value usually lies between -1 and +1. A value close to +1 means a strong positive relationship. As one variable increases, the other also tends to increase. A value close to -1 means a strong negative relationship. As one value increases, the other tends to decrease. A value close to 0 means there is little linear relationship. Suppose the result is correlation with study hours is 0.76. A simple interpretation would be students who studied more hours generally tended to receive higher final scores. So this is a simple interpretation. Notice the words generally and tended. We are not saying that every student who studies more will definitely score higher. A correlation value is useful, but we should also inspect the relationship visually. Create a scatter plot. Before running the cell, predict the pattern. If the correlation is positive, we may see the points rising from left to right. Now run the cell. Look at the overall pattern. If students with higher study hours generally have higher scores, the points should show an upward tendency. However, the points will probably not form a perfect straight line. Some students may study fewer hours and still score well. Others may study many hours and receive a lower score. This tells us that study hours are not the only factor influencing performance. Other possible factors include previous knowledge, quality of study, sleep, attendance, stress, teaching quality, access to resources, and examination conditions. We can add a trend line using Seaborn's reg plot. This line shows the overall linear trend. If it slopes upward, the relationship is positive. If it slopes downward, the relationship is negative. If it is almost flat, the linear relationship may be weak. However, the trend line is a summary. It does not pass through every point, and it does not perfectly predict every student's score. This is one of the most important lessons of day 9. Correlation does not prove causation. So let me write this out. Suppose student study hours and final scores have a positive correlation. Can we immediately conclude that additional study hours cause the higher scores? Not necessarily. There may be other explanations. For example, highly motivated students may both study more and attend classes more regularly. Previous knowledge may influence both confidence and study behavior. Some students may report their study hours inaccurately. The relationship may also work in a more complicated way. Correlation tells us that two variables move together. It does not prove that one variable directly causes the other. Let us consider another example. Ice cream sales and sunburn cases may both increase during summer. This does not mean that ice cream causes sunburn. The hidden factor is hotter and sunnier weather. Hot weather increases both ice cream purchases and time spent in the sun. The hidden factor is sometimes called a confounding variable. For this lesson, remember the simpler statement. A high correlation is a clue, not proof. So let me write it out. Another common mistake is assuming that a high correlation guarantee accurate predictions. Even when two variables are strongly correlated, individual observations can still vary considerably. Suppose the correlation between study hours and final scores is 0.75. That is a fairly strong positive relationship. But two students who both study for 4 hours may still receive very different scores. Correlation summarizes an overall relationship. It does not guarantee an exact prediction for every individual. Later in this series, when we build machine learning models, we will evaluate predictions more carefully. We will not rely on correlation alone. Correlation usually measures a linear relationship. That means it looks for a pattern that can roughly be represented by a straight line. But some real world relationships are curved. For example, imagine that both very little sleep and too much sleep are associated with lower performance, while moderate sleep is associated with better performance. This relationship may form a curve. A simple correlation value may fail to represent it properly. That is why we should always combine numerical statistics with visualization. The number tells us part of the story. The chart helps us see the pattern. We can calculate correlations between several numerical columns at once. First, select the numerical columns we want. Use only the columns that actually exist in your dataset. Before running the cell, predict which variable may have the strongest relationship final scores. With final score, it could be study hours, attendance, or previous score. Now run the cell. The diagonal values are always 1 because each variable is perfectly correlated with itself. The other values show relationships between pairs of variables. For example, the cell connecting previous score and final score tells us how strongly those two columns move together. A heat map, a heat map makes the correlation matrix easy to understand. Before running the cell, predict what and not equal to true will do. It will display the correlation values inside the heat map cells. The argument fmt.2f displays each number using two decimal places. Now run the cell. Look for strong positive values, negative values, and values close to 0. Do not simply select the largest number and call it the cause of final performance. The heat map shows associations, not explanations. Also remember that correlations can be influenced by outliers, missing values, small sample sizes, incorrect data, and relationships that are not linear. Let us now place the key statistics from today into one clear code cell. Before running this cell, pause and answer which value describes the center, which values describes the spread, which values describe relative position, which value describes the relationship between two variables. Now run the cell. Here is the conceptual mapping. Mean, median and mode describe center. Range, variance and standard deviation describe spread. Percentiles describe relative position. Correlation describes how two numerical values variables move together. Possible outliers tells us which observations deserve investigation. Now it is time for today's learner challenge. Your task is create two small lists with same mean but very different spread. Then explain the difference in one sentence. Do not immediately copy the complete solution. Start by creating the first list. For example, list 1 equal to 48, 49, 50, 51, 52. Now create a second list with the same mean, but values that are much farther apart. Then calculate the mean of both lists, the range of both lists, and the standard deviation of both lists. You can use np.mean, np.std, max, min. Pause the video and complete the challenge. Let us discuss one possible solution. The two lists have the same mean of 50, but the second list has a much larger range and standard deviation. A one sentence interpretation could be both groups have the same average, but the second group is much less consistent because its values are spread much farther apart. That is the kind of explanation we want. Do not only write list 2 has a higher standard deviation. That is technically correct, but it does not explain the practical meaning. Here is another possible pair of lists. Both lists have a mean of 70. However, the first list is tightly grouped. The second list has very large variation. You can experiment by changing the values while keeping the same mean. This will help you develop intuition about center and spread. Now let's discuss the common mistakes from today's lesson. So first mistake is treating the mean as a complete story. The mean may be influenced by unusually high or low values. Always compare it with the median and inspect the distribution. Mistake 2 is ignoring spread. Two datasets can have the same mean, but completely different levels of variation. Always ask how widely the values are distributed. Third mistake is automatically deleting outliers. An outlier may be an error, but it may also be a rare and important observation. Investigate before removing it. Fourth mistake is treating percentile as percentages scored. The 75th percentile does not mean that a student scored 75%. It describes the student's position relative to the dataset. Fifth mistake is assuming correlation proves causation. Two variables moving together does not prove that one causes the other. Sixth mistake is assuming high correlation means perfect prediction. A strong overall relationship can still contain substantial individual variation. Seventh mistake is looking only at numbers. Always combine statistical outputs with charts and domain understanding. Before we finish, choose one important output from today's notebook. It could be the mean, the median, the standard deviation, a percentile, an outlier, or the correlation. Now explain it in one sentence without technical jargon. For example, most students scored around the low 70s, but there was still a noticeable difference between the stronger and weaker performance. Or, students who studied more generally scored higher, although study time alone did not completely explain the results. This sentence is your learner evidence for day 9. Let us recap what we learned today. Mean, median, and mode describe the center of a dataset. The mean is the average, but it can be affected by extreme values. The median is the middle value and is often more stable when outliers are present. The mode is the most frequently occurring value. Range, variance, and standard deviation describe spread. The range compares the minimum and maximum. Variance and standard deviation consider variation across all values. Percentiles describe the relative position of values. The 25th, 50th, and 75th percentiles help us understand the lower quarter, middle, and upper quarter of the dataset. Outliers are unusual values that require investigation. They may be errors, rare cases, or important signals. Correlation describes how two numerical variables move together. But correlation does not prove causation, and it does not guarantee reliable prediction. The most important skill from today is not calculating these values. Pandas and NumPy can calculate them instantly. The important skill is explaining what they mean in the context of the problem. Before ending the lesson, answer these two questions. What new capability did we gain on day 9? A strong answer would be we learned how to summarize the center, spread, relative position, and relationships within numerical data. Second question is which output and limitation should you be able to explain without notes? A strong answer would be I should be able to explain correlation and remember that it does not prove causation or guarantee an accurate prediction. That completes day 9 of our data science sprint. Today, we learned how to understand statistics without becoming trapped in complicated mathematics. We used mean, median, and mode to describe typical values. We used range, variance, and standard deviation to understand spread. We used percentiles and box plots to inspect relative position and possible outliers. Finally, we use correlation and scatter plots to study relationships between variables. In the next lesson, we will build further on these ideas and continue converting raw data into useful conclusions. Make sure you save your notebook with the same name, day underscore 09 underscore statistics underscore without underscore heavy underscore mathematics dot IPNB. Complete the learner challenge and add your one sentence interpretation at the end of the notebook. Thank you for watching and I will see you in day 10.